Good morning, everyone. Hope you had a lovely evening. Welcome to our chemistry session this morning. If you were with us yesterday, then welcome back. If you're new, welcome to the My Tutor online school. It's really good to see you here with us. We hope that you've signed up to the online school, and then that way you can see a full picture of the timetable for this week and get an idea of how to access lots of the content. This session is a GCSE Chemistry session on Fullerenes and metallic bonding, and it will be an hours-long session led by our chemistry tutor, Aman, who studies medicine at King's College London and has done over 150 lessons with my tutor. So, as I said, these sessions last an hour, and we have 45 minutes for the teaching of the lesson, and then 15 minutes at the end for questions. You can send questions through in two ways, either through the chat, and if you send them through the chat, then Aman can see them herself, and if you send them through the Q&A, then I can see them and feed them back to her. So final thing from me is to say that these sessions are recorded and you'll be able to access links to them afterwards. Cool, so I'm going to hand over to Aman now.
Thank you. Welcome back, everyone. So today I thought we'd continue with yesterday and make sure we do silicon dioxide, which is one of the giant covalent structures we didn't manage to cover yesterday. And then we'll go into fullerenes, so again, subtopic of covalent bonding, before we start metallic bonding. We won't be looking at the properties of metals today. We'll be doing that tomorrow with alloys and nanoparticles. So just looking at kind of what a metal looks like with regards to its bonding today. Okay, so starting off then with silicon dioxide. So before we go into kind of the structure of silicon dioxide, let's just have a quick recap of what we covered with regards to covalent bonding yesterday. So you'll remember that non-metals covalently bond, only non-metals. And if we look at our periodic table, non-metals are on the right-hand side of this red line, so over here. And these non-metals, they share electrons, and that's one of the key kind of things to remember about covalent bonding. It is the sharing of electrons. They don't donate or give electrons. And because they share electrons, there is no overall charge with regards to non-metals. So now if we think about when we have covalently bonded structures, what do they form? They can form two things. They can either form a simple molecule or they can form a giant covalent structure. And just as a quick aside, someone is asking, is this AQA or EdXL? What I'm covering right now is both the exam boards there. So this is just general things that we need to know about covalent bonding. So covalent bonding can either form simple molecules or it can form a giant covalent structure. Most covalently bonded structures will form simple molecules. So we covered those yesterday, but there are three giant covalent structures that we need to know at GCSE Chemistry, and they are diamond, graphite, and silicon dioxide. And as a side, diamond, also we look at graphene as well, which we'll be looking at today with regards to fullerenes. So the one giant covalent structure we didn't look at yesterday was silicon dioxide. So let's go back then to silicon dioxide. So as I said, it's a giant covalent structure, and what we can see on the screen is that we've got these particles all covalently bonded together. Another aside, someone is asking me, are there more types of giant covalent structures? There are, but the ones that are the most common and the ones that you will be tested on are diamond, graphite, and silicon dioxide. So looking at silicon dioxide, these black bubbles here are silicon particles, and these red bubbles are oxygen particles. So let's look at our periodic table to understand how many bonds silicon should be making and how many bonds oxygen should be making. So if we go to our periodic table, silicon has an atomic number of 14. So remember, that's the number of protons, but it's equal to the number of electrons because we haven't got a charged silicon particle at this point. So there's 14 electrons as well. That means that in its first shell, there are 2 electrons. In the second shell, there are 8 electrons, so 2 plus 8 is 10, and that means there are 4 electrons in its third and outer shell. Exactly, someone has said 284, that's exactly correct. And another person is asking, is silicon dioxide a compound? So remember, the definition of a compound is that it must contain two elements chemically combined. So yes, silicon dioxide is also a compound. So we covered this yesterday, that some simple molecules can be compounds, and so can some giant covalent structures. The only giant covalent structure that is a compound that you need to know about is silicon dioxide. Both diamond and graphite aren't, because they only contain carbon. And remember, that's only one element. Simple molecules, for example, nitrogen is just made of nitrogen. Therefore, it's an element, it's not a compound, whereas water, which is H2O, has hydrogen and oxygen in it, which are chemically combined. So that would also be a simple molecule and a compound. So it's about how many elements are in there and whether they're chemically combined. So yes, someone has told me that the electron structure of oxygen is 2 and 6. So 2 in the first shell and 6 in the second and outer shell. And that's because the atomic number of oxygen is 8. So silicon is 2, 8, 4, and oxygen is 2, 6. So what does that mean? That means that silicon has 4 electrons in its outer shell, and it wants 4 electrons to complete its outer shell. So remember, all nonmetals tend to gain electrons, but when we're binding two nonmetals together, it's the sharing of electrons. So silicon wants to share 4 electrons with another nonmetal in order to get its full outer shell of 8 electrons. Oxygen, on the other hand, only wants to share 2 electrons because it has 6, so it needs 2 more to get 8. So if we go back to our structure of silicon dioxide, as I said, the black blobs are silicon, and we can see it's making 4 bonds. 1, 2, 3, 4. And the relevance of that will become apparent in just a second. And if we look at oxygen, again, it's making 2 bonds, and that's because it has 2 electrons that it needs, or it shares in its outer shell. So that's about the bonding. The second thing to recognize is that giant covalent structures do not have intermolecular forces. The only structure that does is graphite, and that is because graphite has these layers of carbon molecules, and there's intermolecular forces between those layers. So we covered that yesterday, whereas diamond and silicon dioxide don't have any intermolecular forces. They are this structure here. They're all all the particles are bound together. So it's important to remember then, if there are no intermolecular forces, when we are melting or boiling silicon dioxide, there is a very high melting and boiling point because we are breaking covalent bonds. So remember, covalent bonds are very strong. So SiO2 does make quartz, and it does also make glass and concrete. So it can be used in a lot of things. It's also used in sand. It's important that you do know some of the uses of silicon dioxide. Someone is asking me, why does silicon not have 4 bonds throughout? It does, it's just this is obviously only part of its structure. We can't see the whole thing. So it does form 4 bonds throughout, and we're just seeing a part of the structure here. Okay, so we've talked about that it's hard, it has a high melting and boiling point. The next thing to talk about then is the fact that it's hard. And again, that is due to the fact that there are these very strong covalent bonds that need a lot of energy to break. So just like diamond, silicon dioxide is also very, very hard. The third and final property of silicon dioxide is that it does not conduct electricity. And that comes back to these electrons that we discussed. So we said that silicon has 4 electrons in its outer shell, and that oxygen has 2 electrons in its outer shell. So if we think about that, that means if silicon is making its 4 bonds, there are no electrons free to react or to be shared or to carry any charge. Same with oxygen. Oxygen is making its 2 bonds or sharing its 2 electrons. That means there are no electrons delocalized or free to carry any charge. So they're all trapped within the covalent bonding. And someone is asking me, is silicon dioxide soluble? It is not soluble, neither is diamond. Another person is asking, what are the uses of silicon dioxide? As I said, it can be used in glass. It's used in concrete a lot as well. The main use that they test at GCSE Chemistry is its use in concrete and glass. And we're going to come on to an exam question at the end once I've covered all the content that we're going through today. And you can see a typical exam question about silicon dioxide. So just as a quick recap then, it's got strong covalent bonds, no intermolecular forces, and that's why its melting and boiling points are really, really high. It's very hard because of those covalent bonds. They require a lot of energy to break. And the third thing is it does not conduct electricity. Someone is asking, is silicon dioxide using metallic bonding? No, it's not. Silicon dioxide is using covalent bonding because silicon and oxygen are non-metals, so it's all a covalently bonded structure. We call it a giant covalent structure. So as I said, it does not conduct electricity because all the electrons are used in the covalent bonding. That means there are none free to move through the silicon dioxide structure to carry any charge, just like in diamond, where the carbon atoms form 4 carbon-carbon bonds, and that means there's no electrons available. Okay, another person is asking me, why is silicon dioxide not soluble in water? And the reason for that is water, yesterday we covered that water is charged, whereas diamond and silicon dioxide have no charge. So remember I said that most non-metals do not form a charged structure. And the reason for that is because they share electrons. The reason that water is an exception to this rule is because of the way that the bonding occurs. I went through this yesterday. If you want to have a look at it again, the video recording should be up now. Whereas most of the diamond and silicon dioxide structures, they share electrons equally, so there's no overall charge. And that means when we try and dissolve it in water, because there's no overall charge, the silicon dioxide particles can't form bonds with water then to dissolve. So remember, for something to dissolve, it needs to form bonds with water. And so silicon dioxide and diamond can't do that. The other thing to recognize is that when something forms bonds with water, it's almost got to form a stronger bond in order to break its covalent bonds. But covalent bonds are so strong that when it tries to be dissolved in water, it's not energy preferable for the silicon dioxide to break its bonds and form bonds with water, because it's such a stable structure, silicon dioxide, and so is diamond. That means it doesn't want to break its bonds to form bonds with water. Okay. The next thing that someone is asking me then about this is, does that mean graphite is soluble? Graphite is also not soluble. And that's because graphite, although graphite has electrons which are free to move, it also doesn't want to break its covalent bonds. So remember I said there's two things here. So it's got to be charged, and the other thing that we have to remember is it's got to be favorable for that molecule to bond with water. It's not favorable for these molecules to break their covalent bonds and form bonds with water. Would examiners want us to draw a diagram? No, you would never be expected to draw a diagram of diamond, silicon dioxide, or graphite. You would be expected to draw covalent bonding diagrams though. Someone is also asking, does silicon dioxide conduct electricity in solution or when molten? No, because there are never any free electrons. So remember, these electrons are all tied into that covalent bond. It doesn't matter if it's in a solution or molten. They are always completely tied into those covalent bonds. Okay, so the next thing we're going to move on to is fullerenes. So this is a fullerene. So I want to just emphasize here that it's important when we cover fullerenes that we think about graphite. So remember yesterday I said that graphites are hexagonal layers of carbon atoms with intermolecular forces between those layers. If we look at a fullerene, it is effectively one layer of graphite bound together in a football shape. So this one here is the most famous one. It was the first one discovered. It's called Buckminster fullerene. It's made of 60 carbon atoms, only carbon. Therefore, it's an element. Even though they're all bonded together, it is an element. It's only made of carbon atoms. And it's hollow. So that means there are carbon atoms around the outside, but inside there is nothing there. So it's hollow. And the one difference between graphite is the hexagonal and pentagonal rings. So if we have a look here, we have these hexagons. But here we've got a pentagon. So remember, hexagon is 6 sides and pentagon is 5 sides. So a key thing about fullerenes is that they're often made up of more than one type of ring. So this is a hexagon and pentagon mix. You can also get heptagon. Heptagon is 7 rings. And that's just because as we're discovering more fullerenes, they're getting larger and larger, and so more rings are being formed. But there's one key thing I want to show you, and that is that it still forms only 3 bonds. So if we take this carbon atom here, just like in graphite, it only forms 3 bonds. And remember, carbon has an atomic number of 6. And so what that means is that its electron structure, there are 2 electrons in the first shell. Remember, the first shell can only hold 2 electrons, but the second shell has 4, and the second shell is its outer shell. That means carbon is capable of sharing 4 electrons, but in graphite and fullerenes, it only shares 3. So that means there is 1 electron delocalized and available from every carbon atom. And so that means fullerenes can conduct electricity. The other thing I want everyone to be able to recognize is that fullerenes have low melting and boiling points. Now, this is something quite confusing, so I'm going to go through it a bit slowly. So, as we said yesterday, graphite has a high melting and boiling point. And that is because when we try and melt or boil graphite, the covalent bonds between the layers, in the layers, have to be broken, as well as the intermolecular forces between the layers of graphite. In fullerenes, there are also covalent bonds, but there are intermolecular forces between molecules of Buckminster fullerene or fullerenes. So if you imagine another one of these fullerenes is here, and then there's another one, there are weak intermolecular forces between fullerenes. And often, unlike in diamond and silicon dioxide, where you only get one structure of diamond, fullerenes are found as more than one. You wouldn't just have one on its own. So often when we're melting or boiling fullerenes, we only break the intermolecular forces between the fullerenes, and that is why they have a low melting and boiling point. Someone has also asked me, can they be used for drug delivery? We're going to come on to that in just a second. I just want to make sure we all understand the properties of fullerenes first. So just as a recap then, they're made of carbon atoms and only carbon atoms. They have a mix of ring sizes. So we've got hexagons and pentagons in there. Each carbon atom only forms 3 bonds, despite the fact that it has 4 electrons in its outer shell. That means that there's 1 electron free on every carbon atom, which can carry a charge through fullerenes because it's delocalized. And the final thing is that it has a low melting and boiling point because there are these weak intermolecular forces between fullerenes. So hopefully that makes sense. And someone's asking, aren't nanoparticles a fullerene? We're going to go on to that in a second. There's a certain subtype of fullerene that are nano, what we call nanotubes. We're just about to go on to that. Someone's asking me, is this GCSE? Yep, this is GCSE Chemistry. We're currently looking at the subtopic structure and bonding, specifically at fullerenes. What are fullerenes? So fullerenes, that's a very good question. So fullerenes are hollow shaped molecules. They're made of carbon atoms. They're very similar to graphite. So they're completely made of carbon. If you imagine a layer of graphite, that is almost what a fullerene is. And they're arranged in a football shape. There are new shapes now as more are being discovered. But the first one that was discovered was Buckminster fullerene, which is the one on the screen. Someone's asking, are we going to do metallic bonding today? We are. That's one of the last things we're going to cover today. Are there layers in fullerenes? No, there are no layers in fullerenes. Fullerenes are just one almost football type structure, but there can be lots of footballs together, and that's why they have intermolecular forces between them. Someone's asking, what do they actually look like in real life? In real life, you can't see them with the naked eye because are very small, as someone mentioned. We don't count them as nano. We count a specific type of fullerene as nano, but they are very small, so you wouldn't be able to see them. And this is just a structure. So remember, we have covered before that there are limitations of structure diagrams. So this is just to show you that each carbon atom forms 3 bonds. It tends to be a hollow molecule, so inside there's nothing in there, and it tends to have rings of 6 and 5, so hexagons and pentagons, but it won't necessarily look exactly like this. Just like diamond particles, you can't necessarily see their structure. It's all a diagram to help you understand the properties. Okay, does it being hollow affect it? We're going to come on to that in just a second and what that means for fullerenes. So let's move on then. Okay, so someone was asking me about nanotubes and what that means. So the first thing is the definition of nano. Does anyone know what the definition of nano is in terms of the size? Yep, tiny. It means tiny, exactly. So nano means that something is very, very small. In fact, 10 to the minus 9. So if you do GCSE maths, you'll know that 10 to the minus 9 is very, very small. That means that our decimal point will be here, and there'll be lots and lots and lots of zeros before we get to how small it is. Okay, so let's think about carbon nanotubes and what they are. The first thing is that they are cylindrical fullerenes. So remember I said that fullerenes are these hollow carbon molecules and that they're kind of shaped like footballs. Well, actually, carbon nanotubes are cylindrical fullerenes. And what we can see here is that we've still got these layers, that one layer of graphite in pentagons and hexagons, but it's more shaped like a cylinder. And it's still hollow, so inside there's still nothing in there. The other thing to mention is that it does sometimes have a carbon layer here and a carbon layer on that side, so it can mean that it's completely covered, but inside is empty. This diagram is not showing that, just so that it's easier to understand. Okay, the next thing to understand about these is that they are very thin. So the diameter, remember diameter is from one end of the circle to another, is very small usually, but they are really, really long. So this diagram can't show that properly, but they can be really long. And that just means that they can carry a lot more inside them. So if we think about what someone was saying about them being able to deliver drugs, the reason that they're able to deliver drugs is because they're so tiny and they're hollow. So we can put drugs inside them and they can go to specific areas of the body because they're so tiny. So that's really advantageous to the medical field. The other thing is we talked about some of the properties of fullerenes. So one of the things we haven't covered is high tensile strength. So it's really important that we're able to define what a high tensile strength is. And effectively, it's the tension a material can withstand without breaking. So remember, tension is almost like elasticity. So we can stretch it, we can try and hit it, and it won't break. And the main thing here is about strength, stretchiness and elasticity. So this means we can stretch as much as we want and it will not break. So what is it useful for then if it's got a high tensile strength? Well, it's useful for things like tennis rackets and strengthening those and reinforcing sports equipment. So it's often used in tennis rackets. It can be used in golf clubs because of this high tensile strength. Yep, someone said tennis rackets. Excellent, very well done. The next thing to look at is the fact that it has a high electrical and thermal conductivity. So we know already that each carbon atom forms 3 bonds. That means 1 electron is available. It's delocalized and able to carry a charge throughout the structure. What that means then is that it can carry, because it can carry that charge, it has high electrical and thermal conductivity, which means that often these nanotubes are used in electrical equipment. So a lot of electrical equipment will use these nanotubes. They're so tiny, so they can go into small areas, and that's why computers are also getting smaller and smaller. You're less likely to you're more likely to just have a desktop these days without the whole processing unit that we used to have before. And that's because we're using carbon nanotubes in electrical equipment. Someone is asking, should I be writing this down? It's completely up to you. The sessions are recorded, so you can rewatch it again. If you find it useful to write it down, then of course go ahead. Let's look at the other uses. So we talked about delivering drugs. We've talked about electrical equipment. Again, that's because they have this high electrical and thermal conductivity. And the third kind of use that we need to know about is catalysts. So does anyone know the definition of a catalyst? Brilliant. So someone is saying a substance that speeds up a reaction. Brilliant. That is exactly what a catalyst is. So the reason that carbon nanotubes can be used as catalysts is because they have what we call a large surface area to volume ratio. Now, for now, I'm not going to go into the exact specifics of why that is, because tomorrow we're going to be covering nanoparticles and I'm going to show you lots of diagrams to try and help you to explain that. But just as a quick aside, the reason it has a large surface area to volume ratio is all to do with what happens when particles get smaller. So if we imagine a big particle, let's just say this cube here has sides of 10. That means the volume would be 10 times the depth 10, so that's 1,000. And the surface area is 100 because we take one surface and we times it by 6. So 100 times by 6 is 600. Okay, so the surface area to volume ratio of this cube is 600 to 1,000. And then if we take the surface area of a smaller cube, let's just say this is sides of 1, that means the volume of this cube is 1 times 1 times 1, which is 1. And the surface area is 1 times 1, so that's one surface, and there are 6 surfaces on a cube, so it's 6. So the surface area to volume ratio of a smaller cube is 6 to 1. whereas the area to volume ratio of a bigger cube is 600 to 1,000. So to get it down to the same ratio, if we divide by 1,000 on both sides, we end up with 1 on this side and 0.6 on this side. So what we can see is the surface area to volume ratio of a larger cube is 0.6 to 1, whereas a smaller cube has 6 to 1. So that means smaller particles have a larger surface area to volume ratio. So this carbon nanotube over here has a really large surface area to volume ratio. And that means that a lot of reactants can attach to it and react quicker. So remember catalysts, they speed up the reaction. So if we've got a large surface area to volume ratio, that's a lot of surface area available for particles to attach to in order to speed up a reaction. So that's exactly why they're used as catalysts. Okay, so we've covered carbon nanotubes and we've covered fullerenes. The next thing then to look at is graphene. So we covered graphite yesterday, and I think now it's important to cover graphene because there are a lot of exam questions on graphene. And a lot of exam questions ask us what the definition of graphene is. And what I like to stick with is that it's a single sheet of carbon atoms. Someone's asking, where can we rewatch these recorded videos? I believe they're on YouTube. And someone's asking, finds an alternative route with a lower activation energy. Yep, that's exactly what a catalyst is. Okay, so single sheet of carbon atoms. Graphene. So let's go back to what graphite looked like. So we had this layer like this, but there's lots of them joined by intermolecular forces. In graphene, it is just one layer. Someone's asking, what do you think we need to remember for carbon nanotubes? Okay, that's a really good question. I think it's important that you know some of their uses and their properties. So it all relates to the general properties of fullerenes. So the fact they're hollow, they can carry drugs. The fact they have a large surface area to volume ratio, which, as I said, we're going to cover in more detail tomorrow, and the fact that they can carry a charge because of those delocalized electrons. So it's just important to know about their properties. With all of structure and bonding, if you can relate the properties to the use of that structure, you'll be absolutely fine in the exams. So graphene over here, as I said, a single layer of carbon atoms, or a single sheet of carbon atoms. It is 1 atom thick. By 1 atom thick, if we've only got one single sheet, that means this carbon atom will have nothing on top of it and nothing below it. So it is only 1 atom thick. We can see that it's hexagonal, just like graphite. So there's no pentagons. Remember, fullerenes are made of hexagons and pentagons. Graphene only has hexagons. Someone's saying, so it has a large surface area. Yep, so fullerenes have a large surface area. Graphene, it's not a property that we recognize to be important. Okay, the next thing is that it's a better conductor of thermal energy and electricity than graphite. Sorry, someone's asking, is this part of OCR? Graphene is part of all exam boards. Fullerenes, not so much. Graphene is part of all exam boards though. Okay, so it's a better conductor of thermal energy and electricity than graphite. And it's important that we understand why that is. So remember, graphite has these layers of hexagonal atoms, and they've got these intermolecular forces between those layers. Whereas graphene is just one layer. Again, if we look at carbon atoms, they have 3 bonds, which means there's 1 bond or 1 electron free. It's delocalized, so it can carry a charge. But that's the same in graphite. So why can graphene carry charge a lot easier or a lot better than graphite? And the reason for that is that there is less resistance. So in graphene, there is only this one layer of carbon atoms that the charge or the electrons have to carry charge through. Whereas in graphite, we have these layers of carbon atoms, so they have to traverse the layers. So if you imagine, if this is one layer, we've got intermolecular forces, another layer, intermolecular forces. Electrons have to travel through the layers as well as along a layer, through the layers as well as along a layer. So there's a lot of resistance there that the electrons can come across when they're trying to carry a charge in graphite. Whereas in graphene, because it's only one layer, the electrons only have to travel along that layer. They don't have to travel kind of between layers, so there's less resistance. The other thing is that it's very strong, and that's because there are no intermolecular forces in graphene. It's only covalent bonding, so it's a very strong substance, just like diamond and silicon dioxide. And the other thing is that it has a very low mass. Exactly, someone's asking me, why does graphene have a low mass? And it's all because it's only 1 atom thick. If it's one layer and only 1 atom thick, that means it is very, very low mass. There's nothing above it, there's nothing below it. There's very little matter in graphene. So remember, mass is made up of matter. There's very little orbital matter there. Someone's asking, why does traveling between layers result in less resistance? So no, I'm saying traveling between layers results in more resistance. So I'm saying in graphite, because we have to travel between layers, there is more resistance there. Whereas in graphene, there's no layers, there's just one kind of sheet that it just has to travel across. There's no resistance between those layers that it has to travel. Someone is saying, could we only see it with an electron microscope because it is only one cell thick? So yes, it is very, very small, so it would be difficult to see. You can't see it with the naked eye. Can it conduct electricity? It can, because there's that one delocalized electron. So as I said, carbon should form 4 bonds because it has 4 electrons in its outer shell, but in graphene, it only forms 3. And that is simply because there is one delocalized electron, so it only shares 3 electrons with each carbon atom. One delocalized electron from each carbon atom means that it can carry a charge. Excellent. Okay, so that's graphene covered. Let's go on to metallic bonding then, the final part of content that I'll be teaching today. And as I said, we're not going to be thinking about the properties of metals. We're just going to be thinking about how to draw the diagrams for metallic bonding. And it's really important that we are able to draw them. Okay. So here is a metallic bonding diagram that I did earlier. So what we can see here is that we've got cations. So cations are positive ions. Positive ions, another word for that is cations. It doesn't matter which word you use in the exam. If you prefer cation, use cation. If you prefer to say positive ion, use positive ion. And then we've got these delocalized outer electrons. Someone's asking, do fullerenes use metallic bonding? No, fullerenes are made of carbon atoms. Carbons are non-metals, so it's all covalent bonding. There is no metallic bonding in fullerenes. Metallic bonding we're now coming on to now. So fullerenes was all covalent. We've finished covalent bonding, now we're moving on to metallic bonding. Everything I did yesterday and the beginning part of today was all covalent bonding. Okay, so what we can see in this structure is we've got these positive ions and these delocalized outer shell electrons. To understand that, let's imagine that this diagram I've drawn is sodium. So if we go to our periodic table, here is sodium. It's in group 1 and it has 11 electrons in its in its element. And that means in its outer shell, it has 1. And that's because there are 2 electrons in the first shell, 8 electrons in the second shell, 2 plus 8 is 10. That means there is 1 electron in the third and outer shell. So if we go back to our diagram, that means for every positive ion, so for every sodium atom, it will have 1 electron in its outer shell, and that becomes delocalized. So metallic bonding happens between elements of a metal. So we've got here sodium. These are all different sodium atoms. Well, they're now ions because they've become charged. So those electrons they have in their outer shell have become free to move, they're delocalized, and so the sodium has got a positive charge now because it's lost that electron into the structure. So the first thing is they're positively charged ions, they're in regular layers. So what we can see here is they're in regular, nice structured layers. It forms a giant metallic lattice, and that's really important because often in exam questions they ask you what type of structure it is. So remember, we can form giant ionic structures, we can form giant covalent structures, we can form simple molecules, and we can form giant metallic lattices. So for metals, it's a giant metallic lattice. We've got this sea of delocalized electrons. And then the other important thing is that we have this electrostatic attraction. And electrostatic attraction is the attractive forces between the cations and the electrons. Someone is asking, what is a lattice? So a lattice is a way to describe a structure. It's a regular structure, often like this. So that's what the structure that metals have. So it's a lattice, and that's what we use to describe metals. It's just a descriptive word. Okay, and then the other thing to recognize is there are stronger bonds if there are more electrons. So we're going to have a go at drawing the metallic bonding in a couple of metals now. Before we do that, someone is asking, what does delocalized mean? That's a really good question. So delocalized means that an electron is free to move. So in sodium, it has 1 electron in its outer shell. When sodium atoms come together and bond, we get this metallic bonding, and therefore those electrons go out into the structure and they are free to move. They're not bonded or tied in to that each sodium atom anymore. So this electron here, let's just say that is this sodium's outer electron. It's not bonded to it anymore. Instead, it's allowed to move around. It's delocalized and free. Someone is asking, could you explain the positive charge again? Yes, of course I can. So positive charge is because sodium in its electron shell has 2 in its first shell, 8 in its second shell, because it has an atomic number of 11, and then therefore there is 1 in its final and third shell. Now you'll remember that most metals will lose electrons because they want to form an outer shell, just like non-metals, but non-metals tend to gain electrons. If we have a look for sodium, it's easier for that sodium to lose this electron than to gain 7 more to complete its outer shell. So that's why sodium will tend to lose that electron, and therefore it has more protons than electrons. So remember, in a non-charged atom, the number of protons will equal the number of electrons. Whereas in sodium here, if it loses an electron, it will have 1 less electron. So the number of protons will be 1 more than the number of electrons. So now the number of protons will be 11. The number of electrons will be 10. So therefore it has a slight positive charge. So that's why we say that sodium becomes positively charged. Okay, so let's have a go at drawing the bonding then in magnesium and aluminium. So if we go to our periodic table, magnesium has an atomic number of 12. So here's magnesium. So to draw that, that means that it has 2 electrons in its outer shell, 2 in the first one, 8 in the second, 2 in the third. So that is our magnesium. It becomes positively charged, but it loses 2 electrons now. So remember, there are 2 in its outer shell. So when we're drawing the metallic bonding of magnesium, it's really important that we draw 2 electrons per positive ion. So sorry, this one should be joined up. So I'm just going to draw 3 layers. It doesn't matter how many layers you draw. What does matter though is that the number of electrons are the right number to the number of cations or positive ions. So that means we need 2 per ion. So I've got 9 ions here, so that means I need 18 electrons, and they're delocalized, so they don't need to be in any particular place. So I think I've drawn 18 there. So that would be the structure of magnesium. So metallic bonding, the definition of it is that it is strong electrostatic attraction between metals, where you end up with a giant metallic lattice of positive ions or cations in regular layers electrostatically attracted to delocalized electrons. So if you want me to write that down for you, metallic bonding occurs in metals or between metals, and results in a giant metallic lattice structure of positive ions electrostatically attracted to delocalized electrons. Okay, so that would be the definition of metallic bonding there. So the next thing I want to do is look at some exam questions then. So we've covered now metallic bonding, fullerenes, and we looked at silicon dioxide. So let's go on to some exam questions. So this week's question here on metallic bonding. Using a model to explain metallic bonding, delocalized electrons could be thought of as glue. Explain why thinking of delocalized electrons in a metal as glue is a useful model, but one which has a major drawback. So if we go back to our diagram on metallic bonding, we've got sodium there. So remember, that's got 1 electron per positive cation, and that's because sodium only has 1 electron in its outer shell. Magnesium had 2 electrons per positive ion because it has 2 electrons in its outer shell, and aluminium would have 3 because it's in group 3 over here, and that has an atomic number of 13, so it would have 3 electrons per positive ion. Okay, so why can these delocalized electrons be thought of as glue? Does anyone know how we can answer that question? Why delocalized electrons in a metallic lattice can be thought of as the glue? Okay, so the reason they can be thought of as glue is because they attract the cations, exactly as someone said. But the main thing that they're doing is they're stopping the repulsion of cations. So remember, these positive ions can repel because 2 positives will repel each other. But because we've got these electrons in between, they're allowing this electrostatic attraction, and they're actually bringing the positive ions together. So these electrons are thought of as glue because they're holding that structure together. Without those electrons, all those cations would repel, and therefore we wouldn't have this giant structure of this giant metallic lattice structure. Then what is the drawback then of thinking of them as glue? So everyone is saying that the electrons help to stick the lattice together. That's exactly correct, as I just said. The drawback is that we know delocalized electrons can move, whereas glue doesn't move. So remember, glue is a very hard substance once it dries and it holds things together, but we know these electrons are free to move. So the drawback of thinking about electrons as glue is that glue doesn't move, whereas electrons can because they're delocalized. Okay, excellent. Very well done, everyone. So I talked about an exam question on silicon dioxide. So going right back to the beginning of what we covered today, let's think about this exam question then. Welding blankets are placed under metals being welded. They protect the area under the welding. Some welding blankets are made from silicon dioxide, which does not melt when hit by sparks or molten metal. The diagram shows a small part of the structure of silicon dioxide. So remember earlier, someone was asking me, why does silicon not form 4 bonds over here? And that's because it's only a small part of the structure. It's very difficult to draw the whole structure. So welding, it's a process that we do to metals. You have a look here. So it's all described by this picture here, what welding is. And it says some welding blankets are made from silicon dioxide, which does not melt. So what we can see is that welding is often going to release these sparks, which we can see here. And it's saying that these blankets are made from silicon dioxide, which does not melt when hit by those sparks. And we need to explain the bonding in silicon dioxide and why it's a suitable material for making welding blankets. So thinking about the structure and bonding in silicon dioxide then, why is it a suitable material for making welding blankets, do we think? Does anyone know? Brilliant. So someone's saying there are lots of covalent bonds between oxygen and silicon atoms in the structure, which means that a lot of energy would be required to break those bonds and melt silicon dioxide. That is absolutely excellent. So the main thing that the mark scheme would be looking for here is that we say that it is a giant covalent structure, first of all, that is formed. We've got these strong covalent bonds between, or strong covalent bonding between the silicon and oxygen atoms. We can even say that silicon forms 4 bonds with each oxygen atom. And then we need to explain it. So we've described that structure there. We need to explain then. So what does that mean? As someone said, there's a lot of energy required to break those covalent bonds, which means that silicon dioxide has a high melting and boiling point. Okay, and that's why it can be used in welding blankets. Brilliant, well done everyone. Okay, the next thing to think about then, everyone that sent in answers, you're exactly correct, well done. The next question that I have, not this one, is this one. So this is just a question I put in because I get a lot of questions asking me the differences between kind of elements, compounds, mixtures. So I thought we'd have a go at this question then. So which substance is a gas? A, B, C, or D? What do we think? Excellent, I've got lots of answers coming in. C, that is brilliant. So C is the gas, and the reason for that is there's lots of room between those particles. So we covered this on Monday with states of matter. There's lots of room between those particles. They can collide with the sides of the container and with each other. So this is our gas. Very well done. Which substance is a liquid? Okay, lots of answers coming in again. Exactly correct. It is B. Very well done. This is the reason for that is we can see they're not quite in a regular structure and they are able to move over each other. So this is a liquid structure here. So remember, liquid particles can still move, but they're in a semi-regular structure. So yes, that is B. Which substance is an element? Exactly correct, A. And I just want to explain this a bit longer. So this structure here is technically diamond. And the reason it's an element is because it's only made of carbon. So remember, compounds are made of more than one element which are chemically combined. In A, we've only got carbon in there, so therefore it is an element. It's also called a giant covalent structure. And then the final one then must be D, so we're only left with D. Well done, everyone. I think everyone gave in the correct answers, which is excellent. So really well done. So substance made of ions there. So we covered ionic bonding last Friday, and what we can see here is we've got these positive ions or cations with these negative ions. And remember, ionic bonding occurs between a metal and a non-metal. We'll just do one more question, and then we'll go on to the Q&A. So metal is bent and shaped to make a car body here. The diagram below represents how atoms are arranged in a metal. So they haven't drawn the delocalized electrons, they've only drawn the metal atoms there. They're asking which two statements in the table best explain why the metal can be bent and shaped. So we haven't really covered the properties of metals today, but just on what we have covered, which answers do you think are correct then? Okay, someone is saying first and third. That is absolutely correct. So we know that metallic bonding does not have covalent bonds, so we can cross that out. The fact that a metal is shiny is not going to explain why it can be bent and shaped, so we can cross that out. So the only two we're left with are that they're in layers, which we know is correct, and that they can slide over one another. Okay, very well done. I'm going to have a look at the Q&A now.
Hi, Aman. I've seen a few questions that I can feed through to you if you'd like. One is, are fullerenes and carbon nanotubes all giant covalent structures?
Okay, very good question. So they do count as giant covalent structures, yes.
And in what types of reactions are the nanotubes used?
So I'm not quite sure what you mean by that. So usually they can be used as catalysts, and it can be used as electrical products. They're not necessarily used in reactions. They're used more kind of in electrical products, as I said, to help because they have good thermal and electrical conductivity, and they can be used in catalysts because they have a large surface area to volume ratio. So they're not specifically used in a reaction where you would see kind of your reactants and your products as you would in a normal reaction. They're actually kind of used as an aside product, so they wouldn't be used directly in a reaction.
Thank you. Can you describe graphene as one layer of graphite?
Yes, you can. That's exactly one of the definitions that you can use. Just make sure you say it's a single atom thick, and yeah, it is a layer of graphite in hexagonal rings made of carbon.
How can you categorize something as a giant covalent structure, or what defines a giant covalent structure?
That is a really good question. So at GCSE level, the main thing to categorize is that most non-metals will form simple molecules. So most non-metals, when they bind, will form simple molecules. You only need to know the exceptions, which are diamond, because as you know, diamond has that big structure. It's not like a simple molecule binding. Silicon dioxide, which we covered today, graphite, graphene, and the fullerenes. Technically, graphene and the fullerenes have their own mini topic. I class them as giant covalent structures, but you wouldn't be asked what type of structure they are because technically they're classed as fullerenes, if that makes sense. So it's almost a third topic because they're completely separate to simple molecules and giant covalent structures. But because they're so similar to graphite, I class them as giant covalent structures. If in an exam question you are asked of a giant covalent structure, name one of these three. And if you're asked about fullerenes, then we think about fullerenes and Buckminster fullerene and graphene.
Thank you. Do Edexcel exams have all of this in the paper as well?
So when I was looking at the exam boards, I believe Edexcel and AQA do cover fullerenes, graphite, and metallic bonding. I think the OCR exam board don't cover fullerenes, but Edexcel do.
Okay, and then I think there was a question around the drug delivery. If used to deliver drugs, I'm not sure what this means.
Someone's asking how can nanotubes deliver drugs, so
maybe that's similar. Yeah,
I'll answer that one. So remember I said that nanotubes are very, very small. So if we go back to that slide, here we go. They're very small. That means that they can go to a specific area in the body. because we can inject them to wherever they need to go. And the other thing is that they're hollow, so they can contain drugs within inside their molecule. So the two important things are that they're very small, so they can go to a specific area, and that they can carry drugs within them, so which is really good. So it's almost like a vessel for carrying drugs. So that's the reason they're used to carry drugs.
Great, thank you. And then just a few questions asking. So one says, there are lots of covalent bonds between oxygen and silicon atoms in the structure. What does this mean in terms of energy? Would energy be required to break those bonds?
Yes, absolutely. Very good question there. So because of these covalent bonds between silicon and oxygen, there are no intermolecular forces, which means that if we melt or boil silicon dioxide, we're breaking covalent bonds. And as you said, covalent bonds have a lot of energy, or require a lot of energy to break them, because they're very, very strong. So yes, silicon dioxide requires a lot of energy to break those bonds, and that's because there are no intermolecular forces. We have to break covalent bonds to melt it or boil it.
Thanks. How do you know the number of delocalized electrons in bonding?
Yep, excellent. So if you look at your periodic table, when you're looking at metals, it's important to know how many electrons are in its outer shell. So when I showed you the diagram that I'd already drawn, I said this is sodium, and that's because I did 1 electron per ion. So in sodium, the atomic number is 11. That means its first shell has 2, second shell has 8, and third shell has 1. So its third shell only has 1 electron. That means for every positive ion of sodium, there'll be 1 delocalized electron. Whereas for magnesium, there are 2 electrons in its outer shell because it forms 2, 8, 2. So those 2 electrons in the outer shell will be delocalized. So for every positive magnesium ion, there will be 2 electrons. And for aluminium over here, it's in group 3. It's got an electron configuration of 2, 8, 3. That makes the 13. So that means there are 3 electrons in its outer shell. So it would have 3 delocalized electrons per positive ion. And what's really important about that is that as the number of electrons increase, the electrostatic attraction between the cations and the negative electrons also increases. So aluminium will have a lot stronger attraction than sodium because we've got 3 electrons per ion. So there's a lot stronger attraction going on there than in sodium, where there's only 1 electron per ion.
Lovely, thank you. Can you do one more metallic bonding diagram?
Yes, I can. Okay, let's do the structure of calcium then. So calcium has an atomic number of 20. That means its first shell has 2, its second shell has 8, 2 plus 8 is 10, third shell has 8, that makes 18, so its final shell has 2. So we're going to have 2 electrons per positive ion. So if we draw each positive ion first, it doesn't matter how many you draw, what matters is that you have the right number of electrons per positive ion. So if I draw 9, again, they should be regulars, touching each other. So I've drawn 9 positive ions of calcium, and as I said, it's got 2 electrons in its outer shell. That means there must be 2 electrons per positive ion. So I'm looking now for 18 electrons to be drawn, and it's really important that you do that. In an exam question, if they just ask for you to draw a metallic bonding diagram, just make sure that the number of electrons you draw is a multiple of the number of ions, so that it can at least be a metal. So if they ask you to draw just a generic metallic bonding diagram, either draw 1 electron per ion or 2 electrons per ion. Don't draw kind of a random number, because it is important that they are a multiple of the number of cations that are there. Someone is asking, can you draw iron and cobalt as a metallic structure? And someone is saying, I don't understand, is it 2882? It is 2882, that is the correct structure for calcium. And so that means its final shell only has 2 electrons. So you would draw 2 electrons per positive ion, which is what I've drawn here. As I said, someone is asking, can you draw iron and cobalt? So you wouldn't ever be expected to draw them. But what we do know is that iron over here is not one of the common metals. So remember, at GCSE Chemistry, when we cover the periodic table, we'll look at this group in the middle. But at GCSE Chemistry, you will only be expected to draw the metallic diagrams of the first kind of 20 elements. You may be expected to draw the electron shells of iron and cobalt. So I'm not going to draw those because it's not relevant to GCSE Chemistry. Are there any other questions?
I don't think there are any other questions that have come through. If you do have any questions, you've still got just under 5 minutes to get them through. But while we wait for some more, shall we just go through another question?
Yeah, exactly. We can. Just quickly, someone's asking me, why is the electron configuration of calcium 2882? Its atomic number is 20. That means the number of protons is 20. And remember, the number of protons is equal to the number of electrons if we're not got a charged atom. At the moment, because we're just drawing the electrons, the calcium is not charged. So its first shell can only hold 2. Remember, the first shell only holds 2 electrons. The second shell holds 8. The third shell holds 8. 8 plus 8 is 16, plus 2 is 18. That means its fourth shell must have the final 2 electrons that make 20. So calcium has an electron configuration of 2882. Someone is asking, how do you know what charge a transition metal is? We will be covering that tomorrow. Could you go back to the definition of metallic bonding? I will do. Will you cover polymers and alcohol at some point? That's not within this topic. I may cover it in the future. When a nanotube is used to deliver drugs, what happens to it after it finishes its job? Does it remain in the body or dissolve? That's a really good question. Usually they can be excreted out of the body. So that's another thing that makes them really useful. So some of them dissolve depending on which one they are, and some of them can just be excreted out. Why are copper and chlorine decimals? What you're looking at. I'm not sure where you're seeing decimal. Oh, over here. Okay. That's just the periodic table I've chosen. It's to do with the number of neutrons changing in copper because it can become an isomer. We will cover that in a later subject and later lesson, but for GCSE Chemistry, you wouldn't be given a decimal. That's just the periodic table I've chosen, sorry. Okay, let's go to an exam question. But before we do that, I will just go back to metallic bonding for the person that was asking for the definition of metallic bonding, which is here. Okay, metallic bonding occurs between metals and results in a giant metallic lattice. It's a structure of positive ions electrostatically attracted to delocalized electrons. Okay, let's go to an exam question then. All right. An aeroplane contains many miles of electrical wiring made from copper. This adds to the mass of the aeroplane. It's been suggested that the electrical wiring made from copper could be replaced by lighter carbon nanotubes. What does the term nano tell you about the carbon nanotubes? So we covered this earlier. What does the term nano mean? Very small, excellent, very well done. Someone's asking, how can carbon nanotubes be removed from the blood if they're very small? So we don't go through and physically remove them. They can be excreted or they become absorbed. It depends on which type of carbon nanotube it is. They're not harmful to the body because they are not reactive. Remember, they don't have a charge. Good, so 10 to the minus 9. Like graphite, each carbon atom is joined to 3 other carbon atoms. Explain why the carbon nanotube can conduct electricity. Why can carbon nanotubes conduct electricity? Yeah, brilliant. There are delocalized electrons which can carry charge throughout the structure. Very well done, everyone. That's exactly correct. So because it's only forming 3 bonds, there's a 4th electron. So remember, the atomic number of carbon is 6. So that means its electron structure is 2 and 4. So it has 4 electrons in its outer shell, which can share electrons with other carbon atoms, but it's only sharing 3. And that means that there is a delocalized electron which can carry a charge through that structure. Very well done, everyone. Okay, so I think that's it for the exam questions today. Tomorrow, as I said, we'll be going through the properties of metals, alloys, and nanoparticles in more detail.
Right, thanks, Aman. Thanks everyone for joining us. There will be, as Aman just said, a chemistry session tomorrow at 9:45. So looking forward to see you all there. And you can also watch the recording of this session on the YouTube channel. So thanks, guys, and hope to see you tomorrow. Bye.
Bye.